Ağlamışlar.
All right. Good morning. Yes. Now, my name is Nefer again, right here. I'll be presenting 4 lectures on the standard model. In these lectures, I'll be mostly how is my voice level? Is it okay? I feel like I am too loud. In these lectures, I'll be mostly following the textbook by Gordon Kane. It's an advanced undergraduate level textbook. Alright, so I will try to keep these lectures at the advanced undergraduate level, or maybe beginning graduate at some points. So it will be actually at a level which is more elementary compared to the lectures you've been seeing the last 2 days. Now, for additional reading, there are 2 review papers or lecture notes that I recommend. The first one is more standard, and I actually used it in some parts of the lecture by Noves. This is archive reprint number. The second one is the lecture notes by Willenbrock is more for theory-oriented students. These lectures cover some aspects of the standard model which I won't have the opportunity to cover here. So this one is a little bit more advanced. It will be, you can look at it after these lectures. They will make more sense. And these are just a collection of textbooks that you might want to look at if you haven't. These are all, again, advanced undergraduate or beginning graduate level. And of course, there are more advanced textbooks. Now, here's my outline. I will spend actually almost the entire first lecture by reviewing these concepts: groups, spinors, and gauge invariants. Now, at the risk of boring you, I'll even repeat some of the slides that I showed at the end of the basic concept lecture, because I think I passed over them too quickly the first time. By the way, these lecture notes, I made some corrections, so what you see on the screen won't be exactly the same as what you see on the paper. Also, I rearranged the material a little bit. There are some slides in the end as an appendix. I took them, I included them in the beginning. Alright, so here's the outline. Today in the morning session, I'll make a review mostly. In the afternoon session, I will introduce the standard model, talk very briefly about QCD. I don't know much about QCD anyway, and Kazım Hoca will talk about QCD in 2 lectures on Friday and on Saturday. So I'll be very brief. Then I'll mostly talk about electroweak theory, and continue with Higgs mechanism, and then talk a little bit about cross sections. Now I have to tell you that I won't be calculating any cross sections. Right? I'll just estimate cross sections, whereby estimating I mean calculating to orders of unity, which is fine if you want to understand you know, at a basic level what's going on, but it's of course useless if you want to compare with experiment. So at some point you have to calculate cross sections, and Altu Hoca showed you how to do it. Alright, I will probably won't be able to finish the slides. This grand unification is not the standard model anyway. I'll only talk about it briefly if I have the time at the end. Alright. Now, the standard model of particle physics is the theory that describes 3 of the 4 fundamental interactions that we know, everything except gravity. And it's a very successful theory. It's been the theoretical development has been completed roughly 40 years ago, and ever since then it has been confirmed over and over again. It started to get boring. But we know that the standard model is not the whole story. First of all, neutrino masses have been established experimentally through neutrino oscillations, and to include neutrino masses you have to make an extension of the standard model. It's a simple extension, but still it's physics beyond the standard model. And then there are many theoretical puzzles, such as what keeps the electroweak scale much lower than the Planck scale. Dark matter, standard model doesn't say anything about dark matter. Anyway, so we have reasons to think that the standard model is not the whole story. Now, we expect new physics at the TV scale, which has to do with unitarity violation. I will talk about this in more detail in the lecture on Saturday, probably, Friday or Saturday. So there are reasons to expect that there must be some new physics at the TV scale. So LHC, if nature is not very perverse, and you could imagine a scenario where there is new physics, but it has such properties that LHC misses it. It's probably possible. I mean, theorists have lots of imagination, but it's very difficult to arrange. So most likely, if there is some new physics, LHC will see it. Either the Higgs particle and other stuff, or maybe something else. However, just like Newton's laws haven't lost any of their importance after Einstein, the standard model will continue to be important because we know that it's the effective theory valid up to at least the TV, maybe much higher.
Can I ask something?
Sure.
When will people ever say, like, okay, there is no Higgs, or they will still have this little dot if we never see it in the next experiments?
If there's a standard model like Higgs, Higgs with properties as predicted by the standard model, then LHC should definitely see it. But if you have some new physics, then you never know. Now, the standard model depends on gauge symmetry. It depends on actually 3 separate gauge symmetries: an SU3 symmetry for the QCD part, and SU2 cross U1 symmetry for the electroweak part. I will talk about what this means in more detail. But we see that if you want to understand what the standard model is about, we need to know about these rules, U1, SU2, SU3, and we need to know about gauge invariance, right? Because we are talking about the gauge symmetry. So that's why I have to review these concepts. And of course, in the standard model, we have the matter content, quarks and leptons, which are spin 1/2 particles. So we need to know about properties of spin 1/2 particles. Therefore, we need to know about Dirac spinors. Alright. These slides, as I said, I already showed in the basic concepts lecture, but I will repeat. Now, consider rotation of a vector in 3-dimensional space. The matrices that rotate the vector are orthogonal matrices. The orthogonality condition comes from the length of the vector being invariant. So, for this relation to hold true, for the length of the vector to be invariant, you have to have orthogonal matrices. So we call this group ON. In 3 dimensions is O3, the group of orthogonal matrices. Now, if you set the determinant equal to 1, that means you are excluding reflections, you are only considering rotations. Groups with determinant equal to 1 are called spatial. So we add an S, we call this group SON. Now, in 3 dimensions, you have a 3-parameter group, because you can express a general rotation in 3 dimensions as a combination of 3 separate rotations. You have seen Euler angles in your classical mechanics courses, I guess. But, I mean, you could also have a rotation first in the, whatever this axis is, X direction, then Y direction, and so on. Right? And then you combine them, you get a general rotation element. Oh, by the way, this is an example of a non-abelian group because the elements of the group do not commute. So if you first make rotation about the z-axis, then the x-axis, it will be different from making a rotation around the x-axis first and z-axis later. Right? And well, we'll see other examples of non-abelian groups in a moment. Now, an important concept is the concept of generator of the group. Right? The generator of rotation, as you know, is the angular momentum operator. The angular momentum operator generates an infinitesimal rotation. Right? So from this expression, you can just solve for the angular momentum operator. You take derivative of the rotation matrix and set theta equals 0. So if you do that, you have cosines here. From the cosines, you get 1. Right? So you have this minus I, so you get this expression. Now, if you look at the commutation relations, here are the commutation relations of the angular momentum operators. You know. Right. So the angular momentum operator generates infinitesimal rotation. If you want finite rotation, you have to apply the angular momentum operator over and over again, which corresponds to exponentiating the operator, where you think of this exponent as a power series. Right? 1 plus I times jz times theta, and then the square, the cube, and so on. So, what I'm saying is that you write an element of a group as an exponential of the generator. Right? And since the rotation group is a 3-element group, you have 3 different generators. A general rotation is the product of 3 rotations. When you take the product of exponentials, you are adding the generators. Because, you know, e to the x times e to the y is equal to e to the x plus y. Right? So, here you have a sum over the generators. So this is a general element of the rotation group. Alright? Now the commutation relations of a group is called the algebra of a group. I mean, I'm talking about Lie groups. And these numbers are called structure constants. For the SO3 group, this is just the anti-symmetric symbol. So it's 1 if you have an even permutation, it's minus 1 if you have an odd permutation. Now let's move on to the group of unitary matrices. This is supposed to be a dagger. Right? So U is a unitary matrix. In n dimensions, the group of unitary matrices is called UN. There are n square independent parameters for the UN group. Right? Now, a unitary matrix has complex elements. So if you have an n by n matrix and each element is complex, you have to have 2 n square elements. But these elements are not independent. because we have a unitary matrix. And you can write a unitarity condition by multiplying the rows and columns of U and U dagger, which gives you n square constraints. And if you subtract n square from 2n square, you get n square. Why is it important? Well, we will see. If you have n square generators of a group, you will have n gauge bosons when you gauge the theory. Right? So it will be relevant. Now, we are in the standard model. We are talking about special unitary matrices. Special means determinant is equal to 1. We had n square independent elements. Now we are adding one more constraint. Determinant equals 1. So we are left with n square minus 1 independent parameters. So you will have n square minus 1 generators for an SQN group. 3 for SQ2, 3 square minus 1, or 8 for SQ3. Right? These generators will be permission, because, well, you see, for U to be unitary, for U dagger times U to be 1, H must be Hermitian. H dagger must be H. And the condition of being traces corresponds to determinant being equal to 1. Due to this relationship, which you can show most easily if you diagonalize a matrix by, a similarity transformation. So, for example, for SQ2, you write the SQ2 group in this form again, exponential of generators. Generators are called Pauli matrices. They are Hermitian and traces matrices. You have a set of 3 Hermitian and traces matrices. This is completely optional. It's not homework. I will give a few homework problems, but this is not one of them. If you are not familiar with SQ2 spin and Pauli matrices, you should convince yourself that taking the exponential of the Pauli matrix like this indeed gives you the most general unitary matrix. You can write a general unitary matrix in 2 by 2 complex space as A, B, C, D, where A, B, C, and D are complex numbers. Then you apply the condition of U being unitary, which gives you something like this. And then you can show that this exponential of the Pauli matrix has the same form as the unitary matrix here. In particular, this relationship will be useful, this convenient relationship. Here, n is just a unit vector denoting some direction. Right? I hat, J hat, K hat, whatever. Alright, so I have talked about SO3, I have talked about SQ2. Now you should notice how similar they are. Right? You look at the commutation relationships. The Pauli matrices satisfy this commutation relationship where, epsilon was the anti-symmetric symbol. So if you take the commutator of sigma 1 and sigma 2, you get sigma 3 with the 1 halves. And the angular momentum operators satisfy exactly the same commutation relationship. Well, you know that the angular momentum operator corresponds to sigma over 2. Now, if the Lie algebra of the two groups are the same, the groups, well, mathematicians will kill me, but the groups will be essentially the same. But maybe there will be a distinction, a global distinction between the groups. Well, there is actually a distinction, which you can see most easily if you take n hat to be equal to j hat. Alright, so we are just looking at the sigma y term. If you just look at the sigma y term, you have the cosines from here. You have the sine terms from sigma y, and you get the rotation matrix. Right? But you have this 1 over 2's here. So this means rotation with angle theta in SO3 space corresponds to rotation of angle theta over 2 in the SU2 space. Right? So when you rotate a vector by angle theta, it corresponds to rotating a spinner which is, well, it corresponds to rotating a spinner by angle θ over 2. That's the distinction between SO3 and SO2. Otherwise, they are the same. Now, what's a spinner? A basic spinner, I'm not talking about drug spinners yet, but our basic spinner is a two-component object. Spin up, spin down. Right? But you cannot say any two-component object is a spinner, right? Any more than you can say any three-component object is a vector. For a vector to be a vector, it should transform appropriately under rotation. For a four vector to be a four vector, it should transform under the Lorentz transformation. And for a spinner to be a spinner, it should be transformed under SU2. That's just the definition of a spinner. And so, I define two-component object called a spinner, and it transforms under SU2 transformation. It rotates in SU2 space. Okay, so far? I hope you are not getting bored. I told you that this would be elementary. Now let's come to the Lorentz group. The Lorentz group consists of 6 generators. 3 for rotations, 3 for boosts. Alright. So what I wrote down in the basic concept lecture was a pure boost transformation. This push and sinh. For rotation you have cosine and sine. For boost you have cosh and sinh. Now, remember we wrote the generator of rotation in terms of the, we wrote the infinitesimal rotation matrix in terms of the generator of rotation or angular momentum operator with this expression here. And from here we solved for the angular momentum operator. I have written here the same expression that I showed you a few slides ago, but it's in 4x4 space. The first row and column is the time element, the rest is the spatial elements. And you can do the same with the generator of boost. You can take the derivative, set the angle equal to 1, and you get an expression like this. Then to understand the structure, you look at the commutation relationships between the generators. And you get these commutation relationships. The one below is the usual commutation relationship for angular momentum. And then you have these ones, which, if you look at these commutation relationships, they are almost satisfied if you set both the angular momentum operator equal to sigma over 2 and the boost operator equal to sigma over 2, with only this minus sign spoiling the whole picture. Alright, so to take care of this minus sign, you can multiply the generator of boost by an I. Alright, so then you have 2 i's, you get minus 1. Alright, so you see that these commutation relationships will be satisfied if J is like sigma over 2, the angular momentum is sigma over 2, and boost is I sigma over 2, but you have another solution, you could also have minus I sigma over 2. What all this means becomes more clear if you look at the combinations J plus IK and J minus IK. So just define linear combinations. Call J plus IK A, J minus IK B. In terms of these new operators, this is just like defining weather operators, okay? J plus, J minus. If you, in terms of these new operators, the commutation relationships separate. You have one set of commutation relationships for A, one set of commutation relationships for B. And the commutation relationships is the commutation relationship for angular momentum, for SU2. So you have two independent SU2s. The Lorentz group gives you two independent SU2s. Therefore, you can define two types of spinors which transform differently under Lorentz transformations. I took this from Ryder. Ryder called this psi and eta. Okay. Now, for type 1, I'm setting B equals to 0. I'm looking at the A terms. So for A terms, J is equal to minus IK, right? Therefore, K is equal to minus I times J. So under the Lorentz transformation, the first type of spinor transforms as follows. Under rotation, you have polymetrics multiplying theta, just the usual expression. Under the boost, you have the same, you just have this additional factor minus I. And the other type of spinor you obtain by setting J equal to IK. So you are switching sign of the boost, therefore you are switching the sign here. Alright, now, so far there is no reason why these two types of spinors, psi and eta, should be related. They are independent spinors. But now, you want to include parity symmetry in your theory. Okay, parity means you are inverting the space coordinates. When you invert the space coordinates, where position goes to minus position, velocity goes to minus velocity, angular momentum being r cross p stays the same. But the boost being, boost has to do with velocity, so the boost changes sign. Right? So under parity, J stays the same, K, the boost, changes sign. And when you change the sign of K, you are switching the sign over here, which means the two types of spinors get converted to each other. Right? Now we can make the connection to physics, but this is all physics. Anyway, explicit connection.
Can I ask a question? I don't quite understand the matrix for boost. Boost generator, I think, should be in terms of momentum, but I can't. I can't make the connection.
Okay. The Lorentz transformation we wrote like gamma minus gamma beta, something like this, right? Beta was in terms of the speed. Then we define the repetitive parameter phi as inverse tangent hyperbolic of beta. So that those phi's you see in the Lorentz transformation matrix, Koch and sinh, has to do with velocity. Alright. Now, as you know, this is the direct equation. In the direct equation, you have gamma matrices. The gamma matrices are objects that satisfy this particular anti-commutation relationship. Gamma mu plus gamma mu is equal to 2g mu. Now, it turns out that you cannot satisfy these commutation relationships with 2 by 2 matrices. You can only satisfy them with 4 by 4 matrices. So, the solution of the direct equation is a 4-component object, whereas the basic spinors that I was talking about were 2-component objects. Alright, so to form a direct spinor, you combine the two types of spinors that I was talking about, right, and together they make up the direct spinor. For reasons that I have shown in the same slide, and I'll talk about right now. These types of spinors are labeled R and L for right and left. Now, if you go to momentum space, the I dot del mu in the direct equation becomes P mu. And then you have to choose a basis for the Dirac matrices. For relativistic particles, the most convenient basis is the one where gamma 0 is non-diagonal. For non-relativistic particles, it would be nicer if you use the basis where gamma is diagonal. Now I'll be talking about relativistic particles here. So I'll be using the so-called Weyl basis. And if you take the gamma matrices as follows, you can just do the matrix multiplication and you obtain the Dirac equation in terms of phi r and phi r. these are coupled, right? So you see that these mass terms couple the right part with the left part, right? But if you take mass to be 0, then the two equations decouple. You have one equation from here, second term multiplies by left, and then this term below multiplies by right. So you have two separate equations. When you solve them, you get sigma dot p hat, which means the spin in the direction of momentum, which is called helicity, is negative for phi L. This is called left-handed, right? As you know, as I've drawn here. If the spin is in the direction of momentum, it's called right-handed. Otherwise, it's called left-handed. So you get a left-handed solution with the minus sign, and you get a right-handed solution with plus sign. Now, remember in the basic concept lecture, I talked about negative energy solutions corresponding to antiparticles. If you switch the sign of energy, then you are switching the sign here. So you see that when you consider antiparticles, the helicity assignment will switch. And so the antiparticle for a left-handed fermion will be right-handed and vice versa. These fermions are two-component objects. They are called wild spinors. They are eigenstates of helicity in the massless limit. Now, if you have mass, then you cannot have eigenstate of helicity because you can make a boost, you can make a Lorentz transformation, and for example, you have right-handed particle, you can overtake the particle, then the particle becomes left-handed in that reference frame. Right? And indeed, when you have mass, you can no longer consider the right-handed part and left-handed part separately. You have to combine them together into a Dirac spinor. Yeah.
How to define where there is a mass for the left-handed, right-handed? How to define if there is a mass particle?
Mathematically or mathematically just take momentum 4 vector, contract it with itself. If you get 0, particle is massless. If you get m squared, particle has mass.
Because the equation changed, the result changed.
Yeah, I mean, of course they change because a massless fermion is not the same as massive fermion. When you have mass, actually you have 2 times degrees of freedom you see here. I mean, a massive fermion is 2-component object. Massive fermion is a 4-component object. Now, well, I'm not going to talk about aerodynamics. Never mind. Alright, so we have these 2 parts of the Dirac spinor. They transform differently under Lorentz transformation. The right-handed part has its minus sign, left-handed part has its plus sign. Right? Now, we want our Lagrangian to be Lorentz invariant. We respect Lorentz invariance. We know energy momentum is conserved. So we have to form Lorentz invariant quantities out of Dirac spinors. Now, the first thing that comes to mind is, let's just take the Dirac spinor, multiply it with its Hermitian conjugate. Right? But that doesn't work because if you multiply psi with psi dagger, you are multiplying phi r with phi r dagger and phi r with phi r dagger, which doesn't give you 0 because of this additional I factor here in front of the boost. So, to form an invariant quantity, you make use of this gamma 0 matrix, multiply psi dagger with gamma 0, this is called Dirac conjugate or adjoint And then if you multiply psi vector with psi, you have this combination, and you can check by just looking at these expressions that indeed now you have a quantity that's invariant under Lorentz transformations. Right? So psi vector psi transforms as a scalar, Lorentz scalar. Now we will define a quantity called gamma 5, an operator called gamma 5. Which is the product of the gamma matrices. And in the while basis, it takes this diagonal form. Now, if you sandwich a gamma 5 between psi bar and psi, you will introduce a minus sign here. Now, under parity transformation, left goes to right. So switch left and right, switch left and right, the sign changes. Right? So now you have a pseudo scalar.
What do we need for that? Why do we need that?
Well, okay. In the standard model, parity will be broken. So, well, that's not a good explanation. You have different terms in the Lagrangian that transform differently, as a scalar, as a vector. Right? But there are also these possibilities. You know, objects could transform as pseudoscalars and axial vectors and so on. So, I mean, they just appear. They will appear. Okay. Now, I haven't shown you this, but you know, just take my word or go through it. If you sandwich gamma mu matrix between psi and psi bar, it will transform as a vector under Lorentz transformation, just like you would expect from this index. If you put an addition gamma 5, it will transform as an axial vector. Vector changes sign under parity transformation. Axial vector doesn't. So, axial means it transforms the wrong way under parity, the opposite. Anyway. So these are called bilinear covariants. Objects that you can form out of Dirac spinors that transform in particular ways under Lorentz transformation. And you will use these objects to write up expressions in the Lagrangian. So, for example, if you have another vector here, you will multiply it with psi bar gamma mu psi so that you get a Lorentz invariant quantity. Alright, now the matrix gamma 5, by the way, is called gamma 5 because in all textbooks, especially people used to denote x4 as the time coordinate. So, not to get confused, they skipped all the time. Called gamma 5, gamma 5. Anyway, gamma 5 is called hierarchy operator. It's the same as helicity in the relativistic limit, in the massless case. Right? But helicity of a particle you can change. You can make a massive particle. You can make a boost and change the helicity. Hierarchy of a particle you cannot change. Now, out of this gamma 5 matrix, you can form projection operators. Just takes the left-handed part and right-handed part of a spinor. You can see it explicitly from this, from this basis, the wire basis. If you form construct the matrix 1 minus gamma 5 over 2, it will just take the left-handed part when it hits the spinor, and if you add 1 plus gamma 5 over 2, will take just the right-handed part. And these projection operators have the properties that we expect from projection operators. For example, if you take the left-handed part of the spinor and then do it again, it doesn't matter, right? You already took the left-handed part. And if you take the right-handed part first and then try to take the left-handed part, you'll get 0, and so on. Well, again, I mentioned this, but I will mention it again. Parity symmetry is broken in the standard model, which means the left-handed part and right-handed parts of the spinners, Dirac spinners, do not interact the same way. More obviously, you have a left-handed neutrino, but you don't have the right-handed neutrino. So that's not parity symmetry. Alright, here's homework for you. You should show these following relationships. Just write psi is equal to psi L, psi is equal to psi L, psi. Which one was that? I don't know. Something like this. Write the same thing for psi bar. And show that first of all, the vector current, this is called vector current because it transforms as a vector, preserves chirality. So left-hand part gets connected to left-hand part, right-hand part gets connected to right-hand part. Oh, by the way, always remember, when you take the anti-particle helicity assignment distribution, so this psi alpha, you can think well, as outgoing fermion or incoming anti-fermion. And if you say anti-fermion, then you should switch the helicity assignment. Well, you should also show that the mass term mixes right-handed part and left-handed part. And finally, when we have left-handed current, it's the same as having vector current minus axial vector current. Here, in doing the homework, you can verify this explicitly, but it will be useful to note that when you take the left-handed projection operator for, when you take the left-handed projection operator to the right of the gamma matrix, comes right. Okay. Questions, please.
Maybe I lost. You said that the left-handed particles are repeatedly the right hand. Did you show where it comes from theory? Because it's predicted, right? It's not an experiment of fact only, I think it's predicted also, right?
When we write the gauge symmetry for the standard model, we said SQ3 color cross SQ2 left cross U1 hypercharge. The meaning of this SQ2 left is that the weak part only interacts with the left-handed fermions and right-handed anti-fermions. So that's just experimental fact. I mean, you build the gauge symmetry of the standard model to fit the experimental facts. You could embed the standard model in a left-right symmetric model, but that left-right symmetry must be broken somewhere because you don't observe it at low energies. Any other questions?
So, what is the meaning of preserving chirality? Is it same type of component must appear in the same term?
Well, I mean, it's just a fancy way of saying in the vector current you have left-handed spinner connecting to left-handed spinner. That's all.
So, what is the importance of preserving chirality for mixing them together?
Well, I mean, we saw when I was talking about viral spinors, in the masses case, the left-handed part and right-handed part were independent entities. So when we mix them, I mean, that corresponds to a mass curve. That it couples the left-handed and right-handed part.
Can we say something about their masses from this term?
Something about?
Something about their masses. Something like left-handed particles have the same mass with right-handed particles. So
No, I mean, let's say we have an electron. The electron is a direct spinor. It's a four-component object. It has both the left-handed part and right-handed part. So they are not separate objects.
But you see from the second line that to get the mass term, you have to mix actually left and right. Right?
yeah.
All right. Now, so kind of to sum up, when you look at symmetries of the standard model, there are additional symmetries, but the main symmetries is first of all, space-time symmetries, Poincare symmetry, which consists of Lorentz transformations and translations. And you know that due to Nefer's theorem, you should have conservation law for each of these symmetries. For translations, you have energy and momentum. For rotations, you have angular momentum. Well, when I was preparing the lectures, I wondered, what about boosts? Are there conserved quantities associated with boosts? Well, of course there are, but the conserved quantity is not very interesting. Or if you write this and divide by energy, you get x minus vt. That's just the position of the center of mass at 0 time. That's conserved, but it's not very interesting. So that's why you don't see it in the textbooks much. Anyway, now the standard model also has gauge symmetry, which are internal symmetries. Right? So now you have symmetries under rotations of internal spaces. You have a U1 symmetry, S2 symmetry, and S3 symmetry. This is a direct product, which means basically you take the tensor product of representations, which means that these are independent spaces. Right? So the standard model has gauge symmetry under S23, under S22, and under U1 separately, but due to spontaneous breaking, this S22 and U1 parts will mix. I will come to that later. Alright, now here's a brief review on gauge invariance. This will be a little bit hand-waving. Alright, I hope John will talk about gauge invariance in a more serious manner. But here, I will just consider as an example first the Schrödinger equation and consider U1 gauge transformation. Now, first of all, gauge transformation is a funny name. It's like a phase transformation. It could be global or local. Here I said global gauge transformation, local gauge transformation, but usually when people say gauge transformation, they understand local transformation. Okay? So we will consider local gauge transformations where this parameter chi is a function of space and time. So you have a wave function. If you rotate it everywhere with a global phase, you know that it's not going to make any change, right? Because if you take absolute value square of psi, the phase disappears. But when you make the phase transformation local, when it's a function of x and time, where the phase can have different values at each point in space and time, then when you use Schrödinger equation, you take derivatives of psi, and you can see that clearly the expression will not be invariant if you replace the wave function by this expression. Right? So here you have second derivative with respect to x, here you have a derivative with respect to t. These will in general be different. So what you do is to make the theory invariant under this gauge transformation is you add a field. Well, here I'm not really talking about field theory, but you add these potentials. These are just the potentials you know from electromagnetism, right? And then you can check that the expression is invariant if you make this gauge transformation, but you also make simultaneously the gauge transformations for the potentials, or scalar and vector potentials. So under these simultaneous transformations, this expression remains invariant. So you can do the same thing in field theory, and you get the same result when you require the theory to be invariant under U1 gauge transformation, where U1 gauge transformation just means this transformation here. Then you need to add a field to keep the theory invariant, which is the photon field. So you can say that the photon field is required by the gauge symmetry. Or you can say, well, I want the photon field, so I impose gauge symmetry. So here is the same thing in more generalized, written in more generalized fashion. In general, you can write a gauge transformation. And then, to keep the theory invariant, you have to add this term to the derivative. Now, the derivative with capital D is called covariant derivative. If you want the theory to be invariant, the derivative should transform like the wave function does. Right? So, since the wave function goes to u times psi, where u is the gauge transformation, the derivative must go to u times derivative. And from this condition, you can work out how this photon field must transform to keep the theory invariant. Right? You can check that these more abstract-looking expressions are the same as what I've shown in the previous slide. All right, now. Yeah.
Sorry, I'm interrupting this section, but I'm confused about billionaires, and so I can concentrate on this.
Okay.
Okay. I wonder that is it right to say that billionaire terms are important because we can determine which term couples with other billionaires, so we can determine interaction in the Lagrangian.
Yeah, I mean, it determines, well, the terms you can write in the Lagrangian are constrained by Lorentz invariance and gauge invariance. Right? So you can only write Lorentz invariant terms in the Lagrangian. So if you have a vector current, it should, you should contract it with another vector and, yeah?
So we want to construct scalar terms from billionaires.
Yeah, yeah.
Okay. Is it only the important question?
That's very important.
Oh, yes, important.
I don't know. I mean, all right. We are dealing with spin 1 particles, so let's write the Dirac Lagrangian. You've seen this. This Lagrangian, just like Schrödinger equation, will not be invariant under U1 gauge transformation. To make it invariant, you introduce the gauge field, right? And then you see how the Lagrangian transforms under the gauge transformation. Well, you see, what makes the theory not invariant was that you had this derivative here. The derivative acted on alpha, and it gave an additional term which includes the derivative of alpha, right? But now you have the photon field, and the photon field also gets transformed as d mu alpha, and when you transform both the Dirac spinor and the photon field, these terms cancel. I mean, this term, which comes from the transformation of the photon, cancels with the term which will come from the derivative acting on this e to the minus I alpha. So that means when you add the photon term, the theory no longer depends on the gauge, which is what we wanted. Gauge symmetry means the theory should stay the same under gauge transformation. Right? Now at this point you should definitely object, because I told you, well, why should we object? Is this theory invariant under gauge transformation or not?
Because Lagrangian is changed.
Yeah, Lagrangian has changed. So what kind of gauge invariance is that? Well, that's because I was too lazy. I didn't write the whole Lagrangian. In the whole Lagrangian, you also have the gauge kinetic term, right? F mu nu, F mu nu. So if you add that term also, then you can show the entire Lagrangian will be invariant under the gauge transformation, right? But the point I want to emphasize is this: the interaction term with the photon and the fermions comes from the gauge symmetry. Right? You just apply the gauge symmetry and it pops out. Alright, so far I was talking about U1 gauge transformations, but the standard model has also SU2 and SU3 gauge transformations. Now SU2 and SU3 are different because they are non-abelian groups. Right? So for non-abelian groups, gauge theory is called Yang-Mills theory. The idea is the same. So for example, for SU2, again you make gauge transformation, but instead of a one parameter gauge transformation, now you have a 3-parameter gauge transformation. You have the polymatrices here, which is written as tau because in physical context, I mean, when we are talking about weak interactions, we define weak isospin, which is just like spin, but in the internal SU2 space defined by the gauge symmetry. We talk about weak isospin, and then the notation for that is usually T or tau. Okay, but these are just polymatrices. And when you gauge the theory, you include a gauge boson corresponding to each polymatrix. Right? So for SU2, since SU2 has 3 generators, you include 3 gauge bosons. This comes from imposing gauge invariance on the theory. Right? You add these terms to the derivative to make the theory gauge invariant. Then you should calculate how should these gauge bosons transform under the gauge transformation to keep the theory invariant. Right? And I will not do it here. I will just state the result. If the gauge boson has these additional terms, the first term is the same as U1 gauge theory. The second term is actually, well, you can also guess, is how a vector transforms. So if the gauge boson transforms as follows, then the Lagrangian remains invariant. The theory remains invariant.
What are the initials here?
Oh, okay.
I guess 2 cycles.
Yeah. So when we are talking about different symmetries, objects will have different dimensions in the different spaces determined by the symmetries. So for example here, this is the Lorentz index, which tells you that your gauge boson is a Lorentz vector. This index I has to do with the Pauli matrices. There are 3 of them. So it's a triplet of SU2. It's 3-dimensional in SU2 space. It's 4-dimensional in regular space time. Other questions?
Actually, how do you calculate that 3?
How do I calculate this?
No, why there are 3 gauge bosons? Why there are 3 of them?
Right, because you are not making one transformation, you are making 3 transformations for a 3-parameter group. So when you make the gauge transformations, you are making 3 different transformations. It's just like in 3 dimensions, when you rotate the object, in general, it's a combination of 3 different rotations, right? So you have to make the theory invariant under all of these transformations. So for this, you need 3 gauge bosons, 1 for each transformation.
And they are not related.
This last question, sorry.
Are they related?
No, I mean there are 3 linearly independent gauge bosons. Okay.
This is just like the rotations in the normal space. You have rotations around X, Y, and Z. Are they related?
No.
Aha. These are rotations inside the internal SU2 ideal spin space. Are they related?
I guess not.
Okay, so 3 linearly independent combinations. You can write different combinations, and we will actually. I mean, we will take combinations of V1 and V2, we'll see. Alright, so here's again, for abelian gauge groups, you have the gauge boson transformed as follows. For non-abelian gauge groups, it's a bit more complicated. I won't actually be using this, alright, but the important thing for us is the expression for the covariant derivative. Right? It's this expression here. Because when we replace the derivative by the covariant derivative in the Lagrangian, we will have these interaction terms between the fermions and the gauge bosons. Here's a point which I don't know if it's, well, let me say it anyway. Now, for spin, you know that you can have spin 1 half, spin 1, and so on. Right? So you can have 2 component objects, 3 component objects, in general 2s plus 1 component. So likewise for SU2, any SU2, you could have 2s plus 1 dimensional representations. So if you are considering, for example, spin 1 object, 3 component object, then of course here you should take 3-dimensional representations of the Pauli matrices. Just like you take 3-dimensional representations of the angular momentum operators. Anyway. Okay. The standard model. This slide I think is in Japanese, right? But you know the particles, right? You understand. And I will talk about these particles in more detail anyway. Now let's just look at the SU2 part.
Question one more. We have covariance derivative for gauge theory.
Yeah.
Also, we face with the covariance derivative in GR. Are they something have the same or? Is there a mathematical similarity between them?
I don't know. Would you like to comment?
Well, as far as I know, it's the same thing. The difference is that in GR you have a space-time space, and there is this connection which kind of defines the derivative in this closed space-time. In this case, it is in the group topology. It is a connection within the group. So geometrically, in this sense, they are exactly the same.
So is it possible to use differential geometry
So there are differential geometric approaches. Is John around here? He can give more detailed information. You should find John.
Well, in GR, of course, you want invariance under general coordinate transformations. Goes by the name diffeomorphism invariance, something like that. It's related concept, but it's not exactly the same, I think. And I don't know. That's why I hesitate. It's essentially the same, okay? Alright, for the SU2 part, you have 3 generators, therefore you have 3 gauge bosons. However, I should tell you that these 3 gauge bosons are not the gauge bosons of SU2 left. And this gamma is not the gauge boson for U1 hypercharge. And the reason is the Higgs mechanism. This part of the standard model, SU2 cross U1, is known as the electroweak part. It gets spontaneously broken by the Higgs mechanism, and due to the Higgs mechanism, the diagonal part of the SU2 left group and the hypercharge gets mixed to give you 2 gauge bosons. One stays massless, is called the photon, the other is massive, is called the Z boson. I will talk about this in the afternoon session a little bit and more on Friday. But still, if you are just counting, there are 4 generators, 3 from SU2, 1 from U1. Now, if you look at the SU3 part, SU3 is not broken. So in one sense it's simpler, in other senses it's much more complicated because of the strong coupling. You have 3 square minus 1, which gives you 8 generators. So you have 8 gauge bosons, which are called gluons. And you can write an element of SU3, just like you did for SU2. You just use the so-called German matrices instead of Pauli matrices. There are 8 of them. And they satisfy a certain computation relationship. Here at ABC are called structure constants. And Kazım will talk more about the properties. Right? And I didn't talk about SU3 gauge symmetry, but it's exactly the same as SU2. You have objects like quartz, which are charged, have color charge. So then you demand gauge invariance. You rotate the quartz in the color space and demand your theory to be invariant, and you get interaction terms. Alright, now about the matter content of the standard model. First of all, if you look at the SU2 part, the weak isospin part, you have singlets. Singlet means it doesn't get transformed under the transformation. So it doesn't have any interaction terms. Therefore, it doesn't feel the SU2 force at all. So the singlet representations will not feel the SU2, the force, the interaction associated with the SU2 left gauge group. That's why it's called SU2 left. The right-hand part of the electron is an SU2 singlet. It doesn't feel big interaction. The left-handed part of the electron pairs up with the electron neutrino to form a doublet under SU2 transformation. This is just like spin. Okay, so it's called isospin to distinguish. This is a spin 1/2 object, isospin 1/2 object, and the third component is 1/2 for the neutrino spin up, isospin up, and minus 1/2 for the electron. And as you will see, this electron and neutrino will be connected by the charged weak gauge bosons. For the quartz, it's the same story as far as SU2 is concerned. The right-handed parts are singlets, left-handed parts form a doublet. Right? But note that there is this extra index here, that's the color index. These objects are all triplets under SU3. Right? So again, you have different spaces determined by different symmetries, and objects have different dimensions in different spaces. So for example, this object, QL alpha, is two-dimensional in SU2 space and three-dimensional in color. Well, each of these are three-dimensional in color space. And also, they are all Dirac spinors, so each one of these is a four-component object in regular space. Questions?
How can we determine that right-handed part are CB and left-handed part is doublet from experiment?
Yes, I mean, even before the people thought of W and Z bosons, there was the Fermi theory of weak interactions, just a four-fermion theory. Right? And experimentally, it turns out that it has vector minus axial vector form, which is identical, your first one, which is identical to left-left coupling. So yes, that's just an experimental fact that you incorporate in the model.
I need the colors now.
Oh, color. SU3 charge is called color. The reason is that for SU3, you have three kinds of charges. It's called red, green, and blue. And when you add them with equal amounts, you get a color neutral object. Alright, so it's just an analogy. Because, when you add red light, green light, blue light, you get white. Alright, so to summarize the metric content of the standard model, you have these following particles. Right? Two leptons transforming as doublets under SU2. Then the right-handed part for the electron. And you have the quark doublet and the right-handed parts. 15 of them in total. And they have these following charges under SU3 cross SU2 cross U1. The first number refers to color charge. So quark is triplet under color. You have a red upquark, green upquark, blue upquark. The second one refers to SU2. When you see 1 for the non-abelian engaged groups, it means singlet. It doesn't feel the interaction. So leptons don't feel the strong interaction. They are singlets for SU3. Right? This right-handed part doesn't feel the weak interaction. It does feel the hypercharge. Now, of course, at low energies, hypercharge is broken and it combines with diagonal part of SU2L to form electric charge. So at low energies, you recover these electric charges. Well, the hypercharge is arranged to give you the correct electric charges.
What are the three numbers?
These ones.
Yes.
The first one refers to SU3. Okay, so 1 means it's a singlet, color singlet. 3 means it's a triplet, color triplet. Second one refers to SU2. Right? So when you see 2, it means SU2 doublet. When you see 1, it means singlet, doesn't feel the SU2 left interaction. And this last part is the hypercharge. And we will show that this combination, third component of the weak isospin, which will be 1/2 for the upper components of SU2 doublets, and -1/2 for the lower components. When you add that third component of isospin to hypercharge over 2, you get the charge. In different textbooks, you can see different expression because this hypercharge normalization is arbitrary actually. So, if you define hypercharge differently, then this number can change. And of course, this was all for the first family. Then you have 2 more copies of the same. So you have 3 copies of all these particles. I think, well, if I time, I'll come to it at the end, but I think these particles just shout, unify us. So that's well, anyway, maybe I should go into that. So, what's the time? 47? Well, I should then stop here, right? It's okay. See, I say lecture 2 here, so that's fine. I came to where I want to come. All right, that's it for now. We'll continue at 2 o'clock, I guess.